Hi, welcome to this short review on capacitors. I just want to bring in the important points to remembrance. First of all, capacitance stores charges. It's an energy charge storing device. A capacitance is defined as the ratio of the charge to the voltage. Capacitance is measured in farad. Charge is measured in coulomb. And the potential difference or voltage is measured in volts. So simply 1 farad is equal to 1 coulomb divided by 1 volt. Now let's imagine that we try to build a capacitance from a sphere. I'm going to show you that it's practically impossible to get an increased capacitance using a sphere. But we know that the voltage of a charged sphere, conducting sphere, is given by kq by r, where r is the radius of the sphere, k is the constant, which is 1 by 4 pi epsilon naught, and q is the charge on the sphere. So the capacitance of the sphere is now the ratio of charge to voltage. On substituting this, the q's cancel out and you get 4 pi epsilon naught r. Why? Because k is 1 by 4 pi epsilon naught. So the k in the denominator really flips and becomes 4 pi epsilon naught times the radius. Remember that r is the radius of the sphere. So if we assume that a particular conducting sphere has a radius of 1 meter, let's go ahead and calculate its capacitance. Epsilon naught is the permittivity of free space. It's 8.85 times 10 to the negative 12. And of course r is 1 meter, so I have not included that. And you get 0.11 nanofarad. Remember that nanofarad is 10 to the power negative 9. Now, you're using a sphere of radius 1 meter, which is a huge sphere, yet the capacitance is only 0.11 nanofarad. That is why we have to go for a parallel plate capacitor. Now, what is a parallel plate capacitor? It's just two metal plates, maybe aluminum foils, separated by an insulator between the two plates. The insulating substance is called the dielectric. So you have two conducting plates with an insulator or a dielectric kept between them, as shown in the diagram. Outside the plates, as you can see, the electric field is non-existent, it's zero outside. But inside the plates or between the plates, the electric field is given by sigma by epsilon naught, where sigma is the surface density of charge. So the electric field between the plates is E sigma by epsilon naught. Sigma is the surface charge density, which means it is the total charge on the plates divided by the area of one plate. So again, we're taking the charge on one plate divided by the area of one plate. And so on substituting, but before that also, you see, intensity of electric field between the plates can be written as the voltage between the plates divided by the distance between them. D is the distance between the plates. So putting these two equations equal to each other, and then substituting for a sigma as Q by epsilon naught, you get this equation, and of course you can divide Q by V, and you just got to divide A epsilon naught by D. But Q divided by V gives you capacitance, and therefore you get the formula for a capacitance of the parallel plate capacitors A epsilon naught by D. But with a dielectric or an insulator between the plates, the capacitance increases K times. K, this is a small k, do not confuse it with 9 times 10 to the power 9. No, this is a dimensionless constant, which is called the dielectric constant. It might have a number like 6 for mica. For air, K is 1. So K is the dielectric constant, and it increases the capacitance. Now, let's assume that the area of the plates is 1 centimeter squared. Changing into meter squared, it's 10 to the negative 4. And assuming it's mica, let's say K is 6. And let the distance between the plates be 0.1 millimeter, which is 10 to the negative 4 meter. On substituting all these into the equation, and calculating, you get 53.1 picofarad. Now, let me also remind you that the dielectric between the two plates in this case is assumed to fill the whole space between the plates. The dielectric, 1, increases the capacitance, 2, prevents sparking between the plates because they are kept so close to each other. If there was no dielectric between them, there would be a complete spark due to the discharge between the plates. And number 3, it helps the plates to be held really close together without the possibility of them touching each other. So that is a parallel plate capacitor. Now, capacitances can be connected in two ways. You can either put them in series with each other or in parallel with each other. As shown in this diagram, the capacitances C1, C2, C3 are in series with each other. How do you know? If you look at the charges, you see that the positively charged plate is here and the negative is here, but the negatively charged plate is connected to the positively charged plate of the next one, and so is it here. So they're connected to oppositely charged plates, and that's how you know they are in series with each other. The most important thing to remember is that when you put capacitors in series, no matter what their values are, the charges on the capacitors will all be the same. The charges are equal, but the voltages to which they get charged are unequal. And when you add all the voltages, so if you add V1, V2, V3, you're going to get the total voltage of the source. Now, with those ideas, you can get a formula for equivalent capacitance as 1 over C equivalent is the sum of the reciprocals of the individual capacitances. So when you put them in series, surely the equivalent capacitance is going to be drastically reduced. In fact, it's going to be smaller than the smallest capacitance amongst them. So if you have a 1 microfarad, a 100 microfarad, and a 1000 microfarad capacitor connected in series, surely the equivalent capacitance is going to be less than 1 microfarad, which was the smallest amongst them. But when you connect capacitors in parallel, the voltages across them are going to be equal. As shown in this diagram, the voltage across C1, C2 and C3, all three of them, is going to be 12 volts, which is the voltage of the source. But the charges on each one of them are going to be different. So once again, capacitors in parallel, the voltages are equal. In this case, to find the equivalent capacitance, just add the capacitances, which means that you will get an increased capacitance, obviously, because you're adding them up. When a capacitor stores charges, definitely it is storing energy. And to find the energy of a capacitor, all we have to do is to find out how much work is done in order to charge it. And the work done is given by the product of voltage and charge. So if we integrate from the initial zero charge to the final caps Q, we're going to get the total potential energy of a charged capacitor. The voltage can be substituted as Q by C, where C is a constant capacitance. That comes out. Q dQ is Q squared by 2, and on substituting the limits, you get the energy of a charged capacitor as 1/2 Q squared by C. But it can also be written as 1/2 CV squared, or also 1/2 Q multiplied by V. Now the quantity called energy density means it's represented by a small u. It's energy per unit volume. So the unit is going to be joule per meter cube. And it is given by 1/2 epsilon naught E squared, where obviously E is the electric field between the two plates. So that is the formula for energy density. Now a simple calculation, if the capacitance is 1 microfarad and it is charged to 2 volts, then you're going to use the formula 1/2 CV squared. 1 microfarad is 10 to the negative 6 times 2 squared, which is 4, gives you 2 times 10 to the negative 6 joules. So we're talking of small numbers here, keep that in mind. But for such a small device in an electronic circuit, that is considerable energy, as we're going to see later on. The introduction of a dielectric between the plates of a capacitor. As you can see from this diagram, initially the electric field is sigma by epsilon naught, but due to the applied electric field, the atoms in the dielectric get polarized. That is called dielectric polarization, in the sense that the centers of the negative and the positive will shift. They become dipoles. But if you watch closely, you see that the negative is towards the positively charged plate and the positive is towards the negatively charged plate. This in effect reduces the electric field between the plates, because the electric field set up by the dielectric is opposite to the applied electric field. So the effective electric field is the difference between them, and that happens to be sigma by K epsilon naught. That means when you introduce a dielectric between the plates of a capacitor, the electric field decreases. It decreases from sigma by epsilon naught to sigma by k epsilon naught, where k is the dielectric constant. So the effective field is decreased from sigma by epsilon naught to sigma by k epsilon naught. And hence the capacitance is actually increased k times. Without the dielectric, it's epsilon naught A by D, but with the dielectric, the capacitance becomes k epsilon naught A by D. Well, in the later chapters, we're going to see that this tiny device called a capacitance has so many uses. You're going to see that it could be used in a rectifier where AC is converted to DC. It's used in an inductance, capacitance, resistance circuit, which is used for tuning purposes. It could be used in a filter circuit. So a capacitor has many uses. Thank you, and I hope this has helped you. Be sure to send in some comments just to encourage me to put more of these videos online. Thank you.